Mapper for MongoDB. So yeah, you want to go?
Yeah, so I'm just going to give a quick overview of what we're going to talk about tonight. First, I'm going to just give a brief overview of what MongoDB is. I'll briefly go into what Object Document Mappers are, or ODMs, and then I'll get into the meat of the presentation, which is going to be about what we worked on, quick demo of it, and how we implemented it using a lot of interesting template metaprogramming techniques in C++. And we'll finish the presentation with a bit of like what we see in this project for the future before thanking and then accepting all of your questions. But please, if you ever have any questions or need any clarification about what we're talking about, please interrupt us. This is meant to be like interactive. So with that, I'm going to give it to Raphael.
All right. Yeah, so for those of you who don't know, MongoDB is a non-relational database. So it differs from like relational SQL databases in that SQL databases store their data as entries in like a table, for instance. So every data entry has a set of columns which are like a fixed data field. You always know what they are. So MongoDB stores data as documents, which are these key value pairs, like the little example document below for like an intern, for example. And these are saved in a data format called BSON, which is kind of similar to JSON, but it's stored in a binary format. And there's some other like extensions that are specific to MongoDB. But the thing about MongoDB is that there's no schema. So documents in a single collection, analogous to like a table for a relational database, can have fields that are either missing or present, or they can have fields of different types. There's a lot of flexibility, but can often be difficult to work with if you're not used to it. And many languages have drivers that interact with the database. So those will provide all the kind of API for inserting or creating documents in the database, as well as other functions. So when you usually work with MongoDB in a C++ project, there's a lot of boilerplate involved. And you're like serializing your objects from C++ objects into BSON documents. You often have to like roll your own version of that every time. And that's bug prone and kind of a hassle.
Yeah, so these problems also existed in other languages, and people set out to create object document mappers, or ODMs, to solve them. So an ODM is basically like a driver in that it provides functionality for querying, updating, and performing aggregations on your data in the database. But it also goes one step further by providing a method of actually converting your objects, like your C++ objects in memory, directly to the BSON documents stored in the database. And this is accomplished via a mapping between collections in the database and your classes in C++. And if you're not familiar, a collection in MongoDB is similar to a table in a relational database. Yeah, so if you've ever used an object relational mapper, this is the equivalent for a NoSQL database like MongoDB. So there are quite a few object document mappers out there today. Probably the one that's most well known is Mongoose, which is the one for JavaScript. But there are also others like Morphia for Java, Mongoid for Ruby, and even third-party ones like Mandango for PHP. That being said, we're introducing Mangrove, which is the first community C++ object document mapper provided by MongoDB itself. So with that, I'm going to let Raphael talk a little bit about the features.
Yeah, so here you see an example class that would be using Mangrove. So you can see like an intern class that has a name, school, a vector of mentors, and other fields. So Mangrove introduces the idea of like a model, and that provides all the Mangrove functionality, including serialization and the CRUD functions, which we'll talk about in a second. And so when you use Mangrove, you basically inherit from this model class, and this provides the functionality. And what's nice is that also kind of defines the schema for the objects you'd be using. So this kind of lets you put in one place what you expect from your data and how it will be formed. And we support serialization for rich C++ objects. So you can have nested like subdocuments in there. You can have like the BSON types, such as regexes and other like special BSON types, as well as all the like some STL containers, including std-vector. And for example, some of us had several mentors for the summer, so you can see we saw that as a vector. Well, also, often an issue with ODMs is that since MongoDB is so flexible with its schema, it kind of runs into problems of C++, which is a statically typed language. So we kind of try to balance that with using the optional type, which is a feature that's kind of slated for C++ 17, but it's available, I think, in Boost and other areas. And this represents a value that may or may not be present. So for instance, not every intern this summer worked on a project. So some of us just work on regular tickets with the engineering team. So then if you store the project field as an optional, Mangrove will basically, if it finds a document that's missing that field, simply manage that appropriately and put in an empty optional. And so Mangrove also provides all the MongoDB CRUD functions. That stands for create, read, update, and destroy, which is kind of like a set of things you can do to the database and documents in the database. You can see, for instance, when you intern double colon find, that's like the Mongo C++ driver's find function. You can put in a query in there, and instead of returning a BSON document like the driver, it'll automatically return an intern object, which is kind of very convenient for using. And we also provide easy functions to save and load individual objects from the database in the kind of, it's called the active record access model, where a single object maps to an individual document in a database, and Mangrove mediates kind of maintains that mapping very nicely. Mangrove also has query and update expressions. So the way MongoDB does its queries, it's in like a BSON-like format, which you can see in the comment here up above, where it's stored kind of JSON-like curly braces format. And not only that, not very natural to C++ programmers, it's also, you have to kind of write it as a string and then hope it works in production and then fix typos, catch them like all at runtime, which is kind of inconvenient. So we wanted to provide all the query functionality, but in these kind of expressions using natural C++ syntax. You can see, you can use like the Mangrove key macro to refer to like a certain field, like the intern's age, and then you can just use the natural C++ operators that's greater than or not equal to create these queries. And then finally, these get implicitly converted. They get implicitly converted into BSON, so you can just directly pass them into any of the CRUD functions very easily. What's also really nice, you have a compile time checking. So you can see down here, I'm comparing an intern's name to a string. And if that was a number, in MongoDB, this would be just fine, and it would do its own kind of comparison based on different types and just kind of fail silently. But here, at compile time, it'll give you a compile time error and tell you this is a mismatch type, which means you have much less errors in production, which is very nice as always.
So I'm going to do a quick demo. So I'm going to do a quick demo of what it's like to use Mangrove in an actual C++ project. So over here, I have a very simple intern class like we were dealing with before. So you have in your intern class a name, a school, a vector of mentors, a department that they work for, and again, an optional project, because not every intern necessarily worked on a project. So the first thing that we want to do to make this intern a model that we can access in the database is we want to inherit from the Mangrove model class. So what this does, and it's templated on the type that you're trying to turn into a model, which I'll talk about later on when we get into implementation. Then we have to register all of these, all these fields with the model, and this is basically telling the model that whenever you save an intern class into the database, these are the fields that I want to include. And what these Mangrove MVP macros mean is that in this particular case, we want the school field in this intern class to be stored in the database with the key school. Mangrove also allows you to customize the name of these fields. So if you wanted to store this school field as an entry with the key S, you can do that as well. But I'm just going to leave it like this for the sake of simplicity. And then we also provide some constructors, one with the project and one without it, and also a default constructor, because the way our serializer works, it takes an uninitialized object and fills in the values as it reads the BSON from the database. So now that I have this intern class and intern model, I created a vector of these intern objects, and I inserted into that vector a list of all the interns here for the summer, the school that they go to, their mentors, the department they work in, and if applicable, the project they're on. If I wanted to store these intern objects in the database, the first thing I would do is create a database connection. So it would look something like this, and this is something that already exists in the MongoDB C++ driver. So this is just some very little amount of boilerplate. And then we want to actually link the model to this connection. So what I do here is I call the static set collection function of the model to be the interns collection in the demo database. So this is basically saying I want all of the CRUD functionality, so the create, read, update functionality of this intern model to be talking to this particular collection or table in a relational sense in the database. So at this point, I can start calling CRUD functions, and it's actually going to be interacting with a real database out there in the world. So first thing we can do is just drop the collection so that we're dealing with an empty slate. I don't want any stale data when I'm doing my queries. And then I want to insert these intern objects into the database. So one of the CRUD functions that MongoDB provides is insert many. So insert many is just a bulk insert of documents, and we've created in Mangrove, the way we implemented it, it accepts containers of type intern, and I'll talk about how we did that later on. But this here will insert all of these objects into the database, and now they're ready to be queried on. So now I can write a query, and let's say I want to find the name of every intern who either has one mentor or who goes to Brown. So the way you would do that in a traditional MongoDB query is like this, where you would have db.interns.find, then a BSON document that's $or mentors array is size 1 or school is Brown. And again, obviously this isn't natural C++. This isn't something that a C++ developer could be familiar with right away. So with Mangrove, you can actually do something like this, where you call the find query function on the intern model, and then we have this expression here, which is Mangrove key of intern mentors dot size 1. So what this Mangrove key macro does is it takes this class member and turns it into a query operand that we can interact with its own member functions and its own overloaded operators. And we can create a query out of it. So this is intern mentors array is size 1, or the intern school equals Brown. So this is the same, even though this is natural C++ syntax, this will get implicitly converted into this BSON query that's eventually passed into the database. And Raphael will talk later about how we actually accomplish that. So the last thing here is this cursor that we got from the find function. This cursor is actually an iterator to an intern object. So what we're able to do is simply just access it via a range-based for loop like this. Let's see it. So for each of the interns in this query result cursor, we can just output its name like we would access any C++ object. So to show you that this works, I precompiled the demo beforehand. And this, in fact, is a list of all of the interns this summer who either go to Brown, just like Raphael, or other interns who don't necessarily go to Brown, like Caitlin or Susan, but these interns have one mentor this summer. And also to show that this is actually talking to the database, this is a MongoDB shell that we're looking at. I can do a find one query on the interns collection and we find myself. So this is something that was stored in the database from the C++ program. And we can also just query the rest of the interns, and we'll find all of the intern objects in the collection, including ones that don't even have projects. So this shows you how the optionals, so this is one particular intern who didn't have an intern, or who didn't have a project. So that project field is simply omitted when it was saved to the database. So that's a basic overview of what it's like to use Mangrove, but now I'm going to talk a little bit about how we actually implemented this. So the first thing is the fundamental building block of Mangrove, and that's the model. So the model was implemented as a class templated on type T. So as most of you are probably familiar, you can use templates to define a class in terms of another type. So if we wanted to create a model with the intern of type intern, you would simply template it on the intern type. This basically gives the model information about the type, so we know what to return when we do queries. So this is a find one query that returns an optional T. We know what type to accept for the inserts. So this will accept T's for the inserts, and then it's also useful in the implementations of other functions. And there are many more functions here that we've omitted. So we go one step further than that with the Mangrove model, and we also intend to inherit from the classes that you want to turn into a model. You're supposed to inherit from the model itself, templated on itself. So that seems kind of weird. That's called a curiously recurring template pattern, or this is called the curiously recurring template pattern. And this is basically what it's called when a class inherits a parent that is aware of the type of the derived class. So by doing this, the class here, so this intern class not only has all of the functionality of this model, but it has the functionality that it has functionality that's aware of its own type, which is very useful for implementing all of these CRUD functions and active record access functions. Any questions about that? Cool. So the next important thing about accessing data through the model is making sure it's actually linked with a real database and that the objects are mapped to real documents in the database. This is accomplished using the _ID type, or the _ID field. So if you've ever used MongoDB, you would know that every single document stored in the database, so basically every entry has a field called _ID. And this _ID field is basically a primary key. It's the key that must exist in every entry and it must be unique. So it's a way of uniquely identifying an entry. So rather than having the user provide that in their user-defined types for their models, we provide that for them in our model base class. Beyond that, this type can, by default, is of type object ID. An object ID is simply just MongoDB's version of a unique identifier. But not every user will necessarily want their primary key _ID to be this object ID. Some people might want to use other arithmetic types. Some people might want to use strings. Some people also might want to do more complex types like an embedded document. This is all supported by the database itself, so we wanted to make sure that we did incorporate it in Mangrove as well. So we let you customize the type of the _ID with a second template parameter called the ID type up here. So then when we define the _ID, we simply provide it as an ID type and not necessarily an object ID. The other thing that we need to make sure exists in the model is an actual connection to a database. So we additionally store a MongoCXX collection here. So a MongoCXX collection is the C++ drivers. It's a C++ driver class that represents a connection to a database collection. So it's basically like a connection to a table in the database. The only problem with this is that this connection is not thread safe. So if you're trying to use the MongoDB C++ driver and you're trying to access the same connection from different threads, you can run into a lot of nasty race conditions. So the way that we resolve that in Mangrove is by adding the thread local storage specifier that was introduced in C++ 11. So what this lets us do is it lets us have, even though this is a static variable, this is a variable that will exist, or that will be different for every thread that the model is used in. So when you're using Mangrove in a multi-threaded application, you can simply set this collection to something new in every thread. Next thing I want to talk about in the model is how we implemented one of the many different CRUD functions that were out there. So like I showed you in the demo, insert many is one of the many different CRUD functions available in MongoDB. Insert many, again, is the bulk insert of documents. And we wanted to make this available in this model class. The only thing is we only really want it to accept containers of type T or iterators of type T. Does anyone know how we can restrict a function to only accept a container of a particular type or an iterator of a particular type? So that we can accomplish this with the C++ technique called SFINI, and I'll get into that. So SFINI it stands for substitution failure is not an error. And that's kind of confusing. This is really just explaining how it works, but not what it actually does. What it really does is it's a method of restricting your function templates to only exist when your parameters have certain traits. So let me try to break that down. So here we have two print val functions. I want the print val function to accept any value that will support this, printing over like this stream overload. But I want arithmetic types to be prefaced with this number string, and I want my non-arithmetic types to be prefaced with this non-number string. So the way that we can accomplish that is, in addition to our first template parameter, we can add this new template parameter called std enable if t. So what this is doing is the std enable if t is a struct that accepts one template parameter, and that template parameter is a bool. It can actually accept two template parameters, but I won't get into that now. But so the first template parameter accepts is a bool, and if that bool is true, then this std enable if t exists, and it means that this overload exists. But if this value here is false, then this whole overload won't exist. And what we can accomplish with that is if we set the bool parameter here to be std is arithmetic t, so we're checking if this t type is arithmetic, then we want to use this overload. And this overload now knows that this is only enabled for numbers. And we can do something similar here at the bottom where we do a similar Boolean parameter except prefaced with this not. So this whole overload is only enabled when this is arithmetic t evaluates to false. Any questions about that? Cool. Sorry? Yeah, I'll talk about that in the next slide. So the C++ standard library provides in C++ 11 this cool header called type traits, which offers a lot of interesting functions such as this std is arithmetic that we use to determine the trait of this type, and also contains a lot of other functions like std is same for comparing two types. So I could, for example, just compare a type with t and only enable it for a certain set of types. And there are a lot of other cool type traits there too, like figuring out whether your types are const qualified, whether they're derived from a certain class, and so on. And yeah, you leverage these traits with std enable if to enable your overloads for certain functions. So something kind of interesting, this is kind of a side note. If you've ever heard of the concepts technical specification, this is what the concepts TS is trying to solve. It's trying to make this kind of gross template metaprogramming way of solving this problem really elegant. So if we were using concepts, which isn't even going to be coming in C++ 17, our code on the right might look something like this, where your print val would just accept a numeric type, where numeric type is some concept of a numeric type. Or for your non-numeric type, you can just template it and require a non-numeric type. So this is a look at like what the future of C++ might be in the next 5-10 years. But we have to go back to reality because the standards committee is still debating about how exactly they want to implement the concepts. So one more thing I want to talk about with this spin-I idea is how this std is arithmetic value is kind of clunky. Not only are we checking if the std is arithmetic and calling it on t, but we also have to access its value member, which just is kind of verbose. So in C++ 17, they provided in the standard library these kind of aliases, which basically just, instead of doing : value after the template struct, you just do std is arithmetic vt. And this was possible because as of C++ 14, variable templates were introduced. So there's now a way of defining a set of variables at compile time using templates. And I'll go into how we actually use that for our iterator and container example in the next slide. So let's go back to the problem that was at hand. We wanted to create an insert many function that would accept a container of one particular type or an iterator of one particular type. So first thing we wanted to do is create two type traits, similar to the traits that we use in the standard library. So I wanted to create a is container of trait and an is iterator of trait. So the way that we can create our own traits is, or one option of doing this is by simply inheriting from one of the traits that exist in the standard library. So this particular trait, this struct is container of, it's templated on a container type, where container type might be something like a std vector of ints, or a std vector of strings, or a std vector of the intern objects we're dealing with. And then the second parameter is just a type name t. And we want this is container of struct to have a value of true when this container contains this t value. So one way we can do that is by inheriting the std is same trait, which has a true value when its two template parameters are of the same type, but false when the two template parameters are not of the same type. So we can take, what we want to do is we want to compare whether or not the container's contained type is equal to this type. So fortunately, all containers in C++, or all containers in the C++ standard library have this value type member, which describes the type that it contains. So we can do the std is same and compare the value type of its container with this t type. So this accomplishes exactly what we want to do. We then want to do the same thing with the iterator. However, an iterator in C++ might not always have this value type member, and that's because in C++, there are a lot of things that can be an iterator. You can have your typical iterator objects, but also pointers can be iterators. So even though pointers aren't actually objects, they still act like an iterator. They can be incremented, decremented, and they can be dereferenced. So we have to find a way to determine the value type of iterators like that too. Fortunately, the C++ standard library also provides this std iterator traits class, where we can pass in any iterator, whether it's a pointer or like just an iterator class, and from that it can determine the value type. So we can do something similar to the container type, except instead of looking at the container type's value type, we look at the iterator traits value type, where the iterator traits is given the iterator that we're checking as a template parameter. That was a lot. Any questions about that? Okay. So, and then the last thing we're going to do before we actually use this in our insert many overload is create these variable templates I was talking about. So this is just an alias. So instead of having to do is container of and then : value, in C++ 14, you can create a variable template where this variable will exist. You can template the variable on these two things, and we'll have this same value. So this is essentially an alias for this longer, long form. So now how do we actually use this? So I have two implementations of insert many that I want to deal with. That's the insert many implementation that accepts a container, and the insert many that accepts a begin and end iterator. So now in the container type, in the container overload here, I can enable this only when is container of v. So is container of, meaning when this container type is a container that contains t, where t is the model's type. So in the intern example, the model will be templated on the type intern. That would mean that this insert many overload would only be enabled when the container contains interns. So that's how we kind of accomplish that. And we do the same exact thing with the iterator down here, except we're using the is iterator trait that we defined. Any questions about that? No. So you'll be calling insert many. So insert many is a static function of the intern model, but you're going to be giving it a container of interns. So for example, this insert many won't accept interns, but it will accept perhaps a vector of interns, a list of interns, or anything that looks like a container and returns interns when it's iterated through. Does that make sense? Yeah. So, with intern containers. Yeah, the parameter is the container of interns, but this function itself will be a static function member, or static member function of that intern class. Yeah. But because we're using the curiously recurring template pattern, the intern class itself can have this insert many member. So if I go back to the model, I'll just go all the way back. So the intern, this insert many function is accessible like this. So you can call the intern model : insert many, then this will accept the container of the interns. And the reason that it has access to that function is because the intern itself inherits the model templated on intern as well as all of its static functions. So it's just a way of consolidating all of this functionality into the intern class itself. Is that any more clear? Okay. Let me go back to okay, great. Last thing I want to talk about with the models and their implementation is how we actually perform the serialization of the fields into the BSON stored in the database. So this is powered by a C++ serialization library called Serial. The Serial is, like I said, a header. It's a C++ 11 serialization library. Very good. It was made by some grad student at USC, I believe. Definitely check it out if you ever want to use serialization, because it's very simple. If you want to make a class serializable in Serial, you simply have to give it a serialization function, or yeah, just a serialize function. So what this lets you do, in our particular case, if we had our intern model, we could create a serialized function like this, and if serial is set up properly, then it will make this intern class immediately serializable. The only thing is with this, we don't really want our users to have to write this serialization function for all of their models. So we included the generation of this function as one of the things that our registering of keys macro does. So next thing, you can tell that this serialize function works on this idea of an archive. So an archive in Serial is the idea behind how serialization is actually performed. The JSON output and input archives, they accept these C++ classes that contain the serialize functions and produce JSON, or they read JSON and produce these objects. And one exists as well for XML. So clearly there's not one for BSON. So, oh, and one more thing. Serial itself heavily uses the concept of spini, which is our way of restricting function templates, to actually define how to perform the serialization for all sorts of different types. So obviously JSON will have different ways of serializing a type depending on whether or not that type is an array, or if it's a numerical value, or if it's a string. So spini is very helpful in that regard. So we went one step further and we implemented a BSON output archive and a BSON input archive. And this is basically a heavily modified fork of this JSON archive, because clearly there are many similarities between BSON and JSON. And in this BSON output archive, we inherited pretty much all of the support for Serial's type, or all this type support that Serial already provides. So support for all of the standard types, all the standard containers like vectors and so on. But we also added support for all of the different BSON types that are out there. The BSON specification specifies a lot of other interesting types that might be useful, such as like regular expressions, timestamps, so on. We also added support for the like upcoming standard optional, which is how we supported more dynamic schemas. And then, like I showed you in the previous slide, the macros that you use to register your keys in a model generate these serialization functions for all your user-defined types. So most of this serialization is kind of just done in the background. The user doesn't really have to worry about what's going on. So with that, I'm now going to pass it on to Raphael, who's going to talk a little bit about how the query and update expressions work in Mangrove.
Yeah. So the main thing with C++ is that there's no really reflection in C++. So if we wanted to get a list of the fields that we want to serialize or refer to in queries and their names, there's no automatic way of doing that. So what we do is we use like the Mangrove make keys macro you saw earlier and the Mangrove MVP macro to kind of store every field that user wants to serialize as this kind of field object that contains a member pointer to the field itself and the string. And I'll go over how that's actually retrieved in the next slide. But then we store like a tuple of all these different fields that we want to serialize inside the base class in this object called fields. And then the idea here is that eventually, once the user wants to refer to these fields, they can just call the Mangrove key macro with the base class and the name, and then we'll retrieve the corresponding field object from the tuple.
That field object is what you use to actually, what you use as query.
Yeah. So here's an example of a small class you may want to serialize. It's like a two-dimensional point that contains an integer x and y coordinates. And you can see the user used the make keys macro and stored the and use the MVP macro for two of the fields and the base class point. And then underneath are the two macros. They're at play here. You can see that the MVP macro is actually rather simple. It creates this MVP class object with the member pointer and the name of the field as a string using this preprocessor kind of pound sign thing. And the Mangrove base namespace alias comes from right here in the make keys macros. That's just the base class itself. And then make keys simply takes all its arguments, which are in this case just these two fields after the base class, and stores them inside this tuple. Although the point of detail, we actually just create a function that returns the tuple. Just we don't have to allocate static storage for it in the class. So it kind of makes the interface clearer. Otherwise, you'd have to put something like in the line afterwards to kind of fill in this storage for this tuple. And here you see an example of the class with the macros evaluated. So it's not too complicated. You just have the two field user specified, and then just this fields function, which returns a tuple of two elements, which contain a representation of the two fields user wants to serialize, x and y. And also there's the serialize function that is generated, which Adam talked about earlier for the work of serial. So once we have our fields, we want to have some way of retrieving them. So if the user uses the Mangrove keys macro I mentioned, they'll be able to get back, they would pass in a field member pointer as the base class and the field name, and it would get back this field object. And the way we end up doing that is we have to somehow statically iterate over this tuple of fields until we find the correct one. And we've tried several methods. C++14 has context for for loops, which sound promising to be able to kind of iterate over every element. Unfortunately, tuples are very heterogeneous. They don't contain all the same type because each field has a different member pointer type. So that just didn't really work. So what we end up doing is using a template parameter recursion. So we had a recursive function, which I'll show in the next couple of slides, that accepted an index in the tuple as a template parameter, and it would kind of recurse on itself and create basically a new version of a new template for the function for every position in the tuple. And that's how we were able to kind of iterate over that fields tuple. And the note of the library Boost HANA provides a lot of very useful functions for kind of doing this kind of tuple iteration very cleanly, but we didn't really want to add a Boost dependency into our whole project and deal with that. So basically, the way this function works, they have, like, for example, three fields here in a tuple, and you can see their indices on the side. The function takes basically three template arguments. It takes a current index in the tuple, the total size of the tuple, and then the member pointer we want. So if the user wants to refer to the age, it would have a member pointer to user age. And then we use some more SNA to kind of create three different versions of this. So I can kind of walk you through the process for this. If the user wants to get, like, the client wants to get the user age field. So for instance, initially we started the base class at the start of the tuple when n equals 0. It's like the first element. And you can see the actual pointer we want down here. And so right away you can see that this is a kind of a pointer to a string member in user, and this is integer, because this is the goal here. So right away we create an SNA version when n is less than m, but the nth field has just a different type in the pointer we want. So we can easily just skip that one. And then next we have another version where n is less than m, so we're still inside the tuple. And then, but the nth field has the same type as the pointer. So these are both integer pointers to members inside user. And so we just do an extra comparison to make sure these are like just actually literally equal. And then if necessary, we skip. So this is not the actual user age field. This is zip code. And finally, n equals 2, you're looking at basically the third tuple here, and it does match. So we return the field object that contains this member pointer. And then it's not shown here, but if we get if the user wants to refer to a field that we didn't decide to register, it would simply go through every element in the tuple until n was equal to m, which meant it kind of exceeded the list, and just we return a null value. So the actual Mangrove keys macro, what it does is it refers to this call if field is present function. And what this does is it calls other functions such as wrap bool and wrap, which I'll talk about in a second, that do the actual iterating, but it uses sFNA to basically only enable this call method if wrap bool iterates over the tuple and successfully finds the right field. That way, if you call this and with like a field that's missing, this would simply fail at compile time through sFNA be disabled. And it's nice because there's also very nice syntax error. The error message is very kind of clear. It just tells you call if field is present failed. There's no call with these kind of arguments, so it's pretty easy to debug. You know exactly that. Oh, that field is missing. And then here's an example of the actual iteration done. So basically, like the 3 stages I talked about. The first one is if you're looking when n is less than m, you can see over here, and has field simply checks if the current field in the tuple has the same type as the base member pointer one over here. And so the simple check if the 2 pointers are like literally identical, and then returns it. Otherwise, it just iterates on n plus 1. So it kind of recurses on a version of the function and looks at the next element in the tuple. And then there's the other version where the current field in the tuple just doesn't have the right type, so we can just right away skip and iterate to the next one. And then there's finally our base case, which is here, where if we've kind of gone through all the elements in the tuple and nothing is there, we return like a null value. Are there any questions? And other ways of accessing fields. So MongoDB allows nested documents, one inside the other. And so the way you'd refer to this is by simply chaining 2 existing member pointers or existing field objects using the kind of, I think it's called the pointer to member access operator. And so basically just take these 2 objects. So for instance, to refer to the zip code field of the adder field of this kind of big user document, you'd simply take user.address or user.adder in this case. Be a typo, it's my bad. And then the address zip code field and chain them together. And what this creates is a field object that points to the zip code, but it also has a customized name which is prefixed with the parent field. So that's how MongoDB refers to nested fields, is like adder.zipcode, similar to C++ syntax and C syntax for structs and whatnot. And then another thing is for like arrays in MongoDB, you can access them, for instance, here by simply putting an index after the name, and that refers to the 3rd element in the array, because MongoDB arrays, like C arrays and so on, are 0 indexed. And so in Mangrove, it's very simple. You just use the C++ array access operator. You can kind of very naturally refer to specific elements in the array. And this will properly return the name scores.to in this case. So now that we have our field objects, we can refer to our fields as our operands in our queries. We want to represent these queries in a natural C++ syntax. And so what we do is we want to combine these fields of operators, not to really do computation on them in the C++, but rather to create these objects that represent expressions, which later get evaluated to BSON and passed into the database. And so what would we do? It would be expression templates is what it's called. So expression templates are a way of representing arbitrary expressions, such as mathematical expressions, or in this case, MongoDB queries for this specific case by constructing C++ objects. So all the construction of the various operands are kind of all put together at compile time to create one final object that gets evaluated when necessary, such as when passing it to the CRUD collection function. And so, for instance, you create different classes for different parts of the C++ syntax. For instance, the comparison expert class, which represents the comparison between a field and a value. So, for instance, if age is greater than 21, then you would create a comparison expert object that accepts two parameters, the field and a value. Or Boolean expression, which ANDs two sub-expressions together, or can OR them, depending on its argument. And so this lets you kind of build up this tree of different expressions. And then what's nice is that these expressions are templated on sub-expressions. So for instance, a Boolean expression can accept any two other like Mangrove query expressions. And then another nice side point is that because we use overloaded operators and functions to create these template parameters, we don't have to actually specify their type. So for instance, we can avoid having something like this would be truly nasty, where you want a Boolean expression, like, oh, what kind of Boolean expression is it? Oh, it's two comparison expressions. Oh, what kind, and so on and so forth. So we kind of avoid this pitfall of templates where you need to know, you have to explicitly describe the full type. It can just be very easily inferred in the syntax. And here's an example of like a Mangrove expression over here and how it gets turned into this kind of expression tree. So how Mangrove key for user age, which would be this MVP object, and then the value 21 gets sent via, you overload the greater than operator to create this comparison expert object that takes these two operands, and then similar for comparing strings for a string field. And then finally the Boolean expression, or we overload the Boolean OR operator, and this creates this Boolean expression that takes these two other expressions and combines them. And finally, when this gets passed to a CRUD function, we take this final Boolean expression object at the top level and convert it into this BSON right here. So for instance, for that example, the two kind of main type of functions that are at play here is, for instance, the greater than operator, which takes a field and a value. And you can see this just basically kind of sticks them together into this one object, this comparison expert object right here, and just returns that with the right operator, greater than in this case. And you can see there's also some basic SFNA going on here. So we created a little MVP trait that checks if this type is a proper name value pair. And otherwise it'd be kind of overloading operator greater than for pretty much any other object in C++, which can definitely mess up your code and namespace and whatnot. And as a point of detail, we use here on type name MVP no op type. So for instance, this is what the 21 would correspond to, the right-hand side. And this is just the type of the field, but without any optionals. So if age was an optional field, it would be an optional of integer. So this kind of unwraps it. And we define no op type to be kind of, just it would be int. And you can see over here something similar with the Boolean AND operator, where you can take two expressions and simply stick them together into this Boolean expression object right here, left-hand side and the right-hand side, and the proper operator string. And again, because these take arbitrary expressions, we don't want to overload operator AND for everything in C++, just queries. So we created an isQuery expression type trait, which again, we just kind of manually overloaded it for every possible expression type that we had, like Boolean expression or comparison expression, have it return true for those. So once we have this big expression object, we're going to convert it to BSON. And this we kind of just use the natural C++ drivers BSON builder object. And kind of the way this works, for instance, this comparison expert of like age is greater than 21, for instance, you can see it follows the pattern of key and then an operand like greater than and then the value. And this simply creates this builder object in the C++ driver like API and simply adds, for instance, the field name here, and then it creates a subdocument and then adds the operator here. A key view kind of creates the key for the current BSON object, and then the value, which I'll talk about in a second, because this is not a C++ driver function. There's some other interesting stuff to do here. And then it simply closes the document and finally returns the finalized value. And the reason append value to BSON is bold is because we have some of a dilemma where if we're appending arbitrary values to the BSON, we're not really sure what they are. Like usually they're integers or strings or BSON types, and that's very nice because you can just call it using the builder object, just .append and then value. But sometimes we actually need to use Mangrove serializing capabilities. If you pass in another user object, you're comparing for equality. For you want to serialize that using the functions we already had that Adam talked about. Or if we're having an array, we want to iterate over each element and then append it accordingly using these options. Or sometimes values can actually be other sub-expressions in the Mangrove kind of query classes. So we want to have a custom like append to BSON function for those. And so how do we kind of distinguish between these different types and have like different implementations for each one? And of course, the answer is more SFNA. And so here's an example of the different signatures that we use for the append value to BSON function and the kind of type traits we declared. So by default, we kind of assume it wants to be Mangrove serialized. So if it's not BSON appendable, and I'll go over the implementation of this next, we create like a is BSON appendable type trait. For instance, here, if it is, we can just very easily append it to the builder, kind of using the default like C++ driver function. If it's iterable, we want to do something special to that. Or if it's an expression type, then we want to do the proper thing for that. And then the default here, if it isn't any of these special cases, we assume it wants to be serialized. And so the is BSON appendable function type trait is kind of interesting because it kind of depends on another class, the builder, having this function append that accepts the right types. It's kind of very indirect relative to the actual type. So the way we actually create a type trait for this is using something called trailing return types, which you can see an example of right here. And what it does is it lets you specify the return type of a function in terms of its parameters. So for instance, if you want to have a multiply function that just multiplies two arbitrary objects of the same type in this example, you might want to say, oh, well, it'll return t, it'll accept t, and then it'll return a times b. You can see like two integers or two doubles over here. But what if you want an integer and a double, for instance? What if you want to have like different types? You don't know what they might be. Or what if a times b is kind of overloaded to something weird and it might be a different type than t? So what you can do is you have two template parameters, t and u, for a and b, and then you say the type is auto here, and you can return, you can put this little arrow and do decal type and have the declared type, which gives you the type of the expression a times b, which is known as compile time. It's just difficult to express if you don't know what it is. But yeah. And so technically, I think in C++ 14, you can omit this, and auto will automatically infer like, oh, you want a times b. Well, what's that? Let me check. A times double, that's a double, so on and so forth. But the reason we're going to use decal type, which I'll show you in just a second, is because it doesn't have to accept one kind of operand. It can accept a comma-separated list of expressions. And it'll only return the last one for the actual type. But if the other expressions happen to fail, then the decal type expression fails to compile as well, which is very useful for these kind of SFNA type traits, where we can have a bunch of expressions we want to test, and then the final value will be something like true. An example here, this is the is BSON appendable trait. You can see here the trailing return type here is going on right here. So ideally, if everything passes, and I'll talk about this in just a second, you want to return true type, which is a container for true. However, first it has to evaluate this expression right here. And what this does is it creates kind of an object of the builder class and tries to append to it this the type that we've given to it. And it puts it all in a decal type. So you just return, so it's not actually being evaluated. It's just more like the kind of various types are being computed. So there's nothing actually there's no implementation here. We don't need implementation because it's only being used for the kind of static type checking. And then, however, if, for instance, the type isn't easily BSON appendable, like an object, like a user or something, this will fail. And then this function is like almost like it's been disabled by enable if. And then you can go to this one right here. It'll go to the next possible overload where you'll just return false type. And then you can see actually using this is BSON appendable just returns the type, either true or false type or true type of the implementation function templated on the type you want. And once again, like Adam talked about, we have a handy templated variable that just takes the value of this. I realize that was kind of complicated. So are there any questions about this? All right. So Adam already talked about how you can use like iterator traits to do something like is iterator of and stuff like that. But in another example, it's a kind of good example of what you can do with this trailing decal type kind of SNA-like expression. So here's an implementation for a type trait is iterable. We want to check, is it something that can be used in a range-based for loop? So you saw in the demo, for instance, for intern I in cursor, right? The cursor was iterable in this sense because you could put it in that kind of for loop and just iterate over it. So what we do is we use this decal type, return type, but we try every possible kind of property of iterator. So it has a begin, and I'm also just including the stud namespace here for clarity. Has an end. You can increment the begin iterator. You can dereference the begin iterator. And then finally, if all these pass, you can return true. You notice, I'm sure you noticed there's like these little voids kind of hanging around. And the reason for this is kind of unfortunate, but because C++ allows you to overload the comma operator, like we actually did in Mangrove for like a list of different conditions in a query, then sometimes if you have these different expressions, it might actually kind of fall into this overloaded comma operator and mess this up. So, but however, overload operators don't work with void. So you can just put in these void kind of things over here, and this will prevent the comma operator from messing things up, which is kind of an unfortunate idiom, but there it is. And then once again, we have this is iterable type trait, which just takes the return type of this function and then the corresponding value templated variable. Any questions? All right, so I'll hand it over to.
Yeah, so there's a lot of Mangrove so far, but there's still a lot that we want to work on for the future. So right now we do support those somewhat unstructured data by allowing optional values. We also eventually want to support even more unstructured data. So if you've ever used stdmap in C++, you know that it's a data structure that contains an arbitrary set of key value pairs. What would be really nice is if we could take BSON from the database that is kind of arbitrary, where we don't really know what fields to expect, and turn that into a stdmap of values that we can access just from C++. We also eventually want to support std variant. The std variant is an upcoming C++ 17 standard library feature that lets you create variables that can be one of multiple types. So one use case for this, as an example, let's say you want to store a grade for a class, for example, as a numerical value, or as a string that is either pass or fail. You could store that grade as a variant templated on int or string, so that way your variant could either be the int, like 0 to 100, or a string that is pass or fail. And if we could support that in our models, that would be really cool, because MongoDB itself supports heterogeneous type or heterogeneous fields where different entries in the same collection might have different types for the same field. So in one field, you might have a grade of 99, but in another one, you might just have pass. We also eventually want to support more meaningful projections. So right now, one of the biggest limitations with Mangrove is that when you get a document returned from a query, such as a find, you're getting the entire document. Now, this isn't really ideal because in a lot of use cases, your documents in the database might be very large. They might have a lot of fields, and if you're dealing with millions of documents at a time, that can cause a lot of overhead if you're only accessing one field in the documents. The MongoDB itself provides a way to project values, just like you can project values in a relational query. But we haven't really thought of a great way to accomplish that projection in the context of a C++ class. Then Raphael will talk a little bit about what else in the pipeline.
Yeah. So another thing we'd like to add is MongoDB has the idea of an aggregation pipeline, which is MongoDB's way of doing MapReduce and other interesting analytics on your data, and that involves a bunch of different pipeline stages and operators. That would be very nice to add to the expression builder, so you can kind of do the queries very naturally and have compile time type checking, because there are a lot of them. They get pretty complicated. And then application level joins. So for those of you familiar with relational databases, often certain parts of a piece of data, like a user's address, will be stored in a separate table, and the user will have like a pointer to the or a foreign key to the within like a specific address in that other table. MongoDB supports something similar, where collections or documents can have references to subdocuments in different collections. And so what we would like to do is when we deserialize these objects from BSON into a C++ object, we'd like to kind of pick up all these subdocuments from everywhere and put them into one single manageable object to work with. And finally, GeoJSON, which is kind of a standard for representing geographical data in JSON, and MongoDB can support that and has some interesting operators to work with that. We'd like to add that support in Mangrove as well.
So before we finish, I just want to thank everyone who made this project possible. So first of all, Matt Cotter, he was one of our mentors this summer. He did a lot of the organizational work behind this project, and he also organized tonight's talk, and he organizes all of the C++ meetup talks. He's great. Jason Carey, who helped us a lot with a lot of the more technical work, like the template metaprogramming techniques. I know you.
Yeah, Jason was great for a lot of the weird template metaprogramming stuff that was being done for the expression builder. And also, Justin Lee, he works on Morphia, which is the Java Object Document Mapper for MongoDB. He gave us some interesting kind of design tips and like what use cases people would expect from it, and that was very helpful for building our project.
All right. The last thing I want to mention is that we're actually launching a developer preview of Mangrove today. So you can go to github.com, MongoDB Labs, Mangrove to check out the source code of this if you're curious at all about if you want to look at the actual implementation details, or if you just want to use this in your own projects. We have some documentation up to, let's see. Yeah, we wrote some nice documentation that you can hopefully get you started really quickly. And yeah, so that being said, are there any final questions? I know that was a lot, so. And you can come up after too. Yes? Mm-hmm. Yeah, so he's asking how are the documents stored when you get them back from the database? So the way that we're actually deserializing these things, let me think. So in most cases, they're going to be allocated on the stack, I would say, because, for example, in our demo here, where we have this query result cursor, and we're getting a value back when we take something from the query result cursor, it's stored in this temporary intern object. So this is stack variable. The way that this works is when it's reading it from the database, it takes an uninitialized intern object and then fills it in. So correct me if I'm wrong, like Raphael or Matt or Jason, but I think in 99% of the cases, these objects will be on the stack. Yeah. Yeah, so a quick summary of what he just said for the recording. Some of the BSON types require that you have an underlying buffer when you accept them from the database, because they might contain data that's not necessarily represented in the model. So those are stored as a shared pointer under the hood in the model, but that's only for very few cases, and those aren't even for types that we recommend users use. But you can also read more about that in the documentation. If you want to check it out. Any more questions? All right. Well, thank you again for coming to the talk. Matt, did you want to say anything?
Thanks everyone for coming. Thanks Adam and Raphael.
All right. Thank you. I'll leave up the URL if you want to write that down of the developer preview if you want to check it out. And if you have any issues